Hello class, and welcome to section 4.1 continued. We're going to begin today taking a look at something called decimal degree form. Decimal degree form is something that we use to do conversions utilizing minutes and seconds, but translating that into degrees and vice versa. Starting with the 1 minute increment, this little tick mark really takes the place of 1 minute. And if I want to convert 1 minute to degrees, essentially I'm going to take 1/60th of a degree, equating that to 1 minute. And then for 1 second, using 2 tick marks, 1 second is equal to 1/60th times 1/60th of a degree, or 1/3600th of a degree. Now the quick example that we're going to go ahead and take a look at to help us understand how this particular type of conversion can take shape will be an example in which I ask you to convert to degrees. Now in order to do this, we're going to go ahead and start with the following type of angle. It's going to be a 275 degree, 10 minute, 30 second value. In order to convert, we're going to do the following. I'm going to start with the whole number degree of 275 degrees and break it apart as such, where that will then be added to 10 minutes, and we're going to convert 10 minutes to degrees, as we saw in the decimal degree form conversion, 1/60th of a degree. Essentially what's going to happen here is the units, minutes divided by 60, which is really in minutes, will cancel. And then I'll add that to the 30-minute increment, or seconds, excuse me, and that will then be multiplied by 1/3600th. Same notation, 3600th, and that's in minutes, times 1 degree. Again, the units will cancel in that regard. So if we do this, 275 degrees plus 10 divided by 60, which of course ends up being 1/6, and I'll go ahead and type that in. The decimal point 0.16 repeating, plus, and then we have 30 divided by 3600, or 3 divided by 360, which ends up being 0.0083 repeating. Putting it all together, we add these up, and we end up with the decimal as such, 275 point. And to make things nice and clean, I'll just go ahead and hit 1/6 plus 3 over 360, or the second answer we can still do. And that ends up giving me 0.175 degrees. So I'll fill that in there as such. So my final answer is 275.175 degrees. Now what we can do is actually check our answer on the graphing calculator in a way in which we actually work backwards to prove that 275 degrees, 10 minutes, 30 seconds was our starting point. So we go to our calculator, and I'm going to go to my mode here. Now my mode is set to radians, but I could also set it to degrees. It's going to work either way. Just for the sake of staying with the same mode here, particularly with degrees, we'll go ahead and change it over to degrees, hit enter on degree, and then I'll type in 275.175. I can hit second, and then the apps button, really looking at second angle. And then you can see there the option 4 feature is converting to degree, minute, second. That's the option that I'm going to go ahead and hit, and it should give me my answer. And that, of course, is degrees, 275 degrees, minutes, 10 minutes, and then seconds, 30 seconds. I could also do this in radians, and interestingly enough, it will still work. So converting it back to radians, I'll hit second enter, and then converting it, again, gives me, of course, what I knew it should have started as, 275 degrees, 10 minutes, 30 seconds. Let's move on to some applications problems. With radian measure, we know that theta equals S over R, where S is the arc length. And if we were to get S by itself, we could simply multiply both sides by R. This is a very important formula, again, that stems from theta equals S over R, helping us understand and calculate what a radian is. This is again used to calculate an actual radian in our derivation in the beginning of 4.1. Example 4. Find the length of the arc that subtends a central angle with measure 120 degrees in a circle with a radius of 5 inches. Let's go ahead and draw ourselves a circle. Okay, our circle on an XY axis. Okay, so we go ahead and observe this particular circle, in which we know that our radius here from center to that point is 5, and our angle created given that particular initial side where I'm highlighting R, and this terminal side, theta is formed in that manner, is equal to 120 degrees. So we use the formula to calculate theta from earlier, if you recall. In order to find this in radians, we take the arc length and divide by the radius. In this case, however, we are not given the s, or arc length, so we have to calculate it. So s would be equal to r times theta. So we go ahead and do an analysis in which we know the r, so 5, and we know the theta, so 120 degrees. Now that would be all fine and good if theta was in degrees. It is not. Theta is always in radians in this particular formula, always. So we're going to have to convert degrees to radians, and we know that we can do this by multiplying by pi over 180, in which the units will cancel. I'll remind you in that particular manner. We'll get the calculator out and do the math. So we got 5 times 120 times pi, and then divide that by 180. So that arc length, 10.47, as an approximation, 10.47, and we're in inches, is the measure of the arc length. If you recall, the arc length is right here in our picture. So S equals just that, 10.47 inches. As we move on, we see that the same formula pops up, S equals r theta. But if we incorporate now another variable, t being time, S divided by t equals r theta divided by t. So we simply divide both sides by time, and this will translate into the following. Very powerful formula, linear velocity. Linear velocity will be equal to the radius times the angular velocity, or v velocity equals r radius times omega. This symbol means omega. And we're going to go ahead and utilize this equation to calculate, in our next problem here, calculate and help us figure out revolutions per minute. I do want to highlight a couple things in this particular formula that's going to help us on various problems. Velocity, or linear velocity, for example, will be unit-wise represented, for example, as miles per hour. This is just a hypothetical. Could be kilometers per hour, meters per hour, or meters per second. There's a variety of units you could use, but it's going to be a pretty typical looking distance divided by time value. R, of course, is your radius. It will be a unit that we want to be the same as the distance, or vice versa. That length of the radius, we may or may not have to convert so that it matches the velocity numerator. And then lastly, the omega. The omega will always be in radians per time. For our purposes, usually it will be radians per minute. To make good sense, again, though, out of the S over T formula from back here, to make better sense out of it, we'll say that S over T is equal to R theta over T. If I were to cross multiply both sides by T, we'll see then that you have the formula S equals R theta. So if you're wondering where it came from, that very much, as you should already know, is the derivation. Example 5. An automobile is traveling at 65 miles per hour. If its tires have a radius of 15 inches, at what rate are the tires spinning in RPMs? RPMs stands for revolutions per minute. So, how do we do the math? Well, A couple of things that we need to highlight. The 65 mile per hour value, that's going to be the velocity. The 15 inches, that's the radius. So my equation, V equals R omega, given the velocity of 65 miles per hour, will be equal to the radius, 15 inches, times omega. Now what has to happen here is, in order for us to calculate the angular velocity, in this case the omega value, it will be in radians per minute. And I know it will be in minutes because my final answer for RPMs has a denominator of minutes. We're going to need to calculate miles per hour, or convert really miles per hour to inches per minute. So 65 miles per hour. We ask ourselves how many feet are in 1 mile. So 1 mile in my denominator, 5,280 feet in 1 mile. Multiply that times, converting from feet to inches. We know that there is 1 foot per 12 inches, or 12 inches per 1 foot, however you look at it. And then lastly, our units for time, because we only have hours to start with, we want to go to minutes when it's all said and done. We know that 1 hour per 60 minutes. So as we'll see here, the miles will cancel, feet will cancel, as will the hours. So my units end up being inches per minute. If you're wondering why I picked inches, well, that's what our radius unit was. And then the minutes, to refresh your memories here, is that our denominator for RPMs is minutes. So we want inches per minute, just that conversion. We'll use our calculator. We'll do the math, taking 65 times 5,280 times 12, and that should equal this decimal, in which when we divide by 60, this is the velocity in inches per minute, 68,640. So I'll write equals 68,640 inches per minute. Well, that's all fine and good, but we still need to, of course, calculate omega. So we will rewrite this equation as such. So 68,640 inches per minute, and that equals 15 inches times omega. Divide both sides by 15. The units, inches, will cancel. I'll write inches. So that cancels. My inches cancel. Now we did talk about the radian being a unitless measure. So let's extend that in this next step. But first, of course, divide both sides by 15. So 4,576. 4,576. Now we did say omega was in radians per minute, and that's exactly how I'm going to write this, which is great. And I know that we talked about radians being unitless. Omega will have this particular type of unit representation. So we're going to go ahead and continue with this. And what's very interesting in terms of the final answer now, kind of separating our work here, our final answer using this omega value, multiplying omega, which again, radians per minute, times, now remember we want revolutions per minute, so we're going to go ahead and write 1 revolution in the numerator, so revolutions per minute. Now that's great, but my radians have to cancel somehow, so we need to think about how many radians are in 1 revolution. If we remember from the beginning, there are 2 pi radians in 1 revolution. Nicely enough, my units are going to cancel. The very, very important thing here to do, or to add on to this, is to put 2 pi in parentheses. I'll show you the difference between parentheses and no parentheses. First, the final answer with parentheses, 4,576. Divide that by parentheses 2 pi, and we end up with a final RPM of 728.29. I'll write that down. And we can actually just simply write RPMs. I do want to just show you the difference, though, if you had not put 2 pi in parentheses. Again, this is my cautionary note here. Do not do this without parentheses, because the calculator does the division of 2 first, and then it multiplies that quantity by pi. So obviously that number is not the same as the real answer here, 728.29 RPM.